So in this video, we're going to talk about p-values and how we can use p-values to come up with a conclusion about our test. So let's first start off with a definition of what a p-value is. So a p-value is the probability of drawing a test statistic at least as adverse to the null hypothesis as the one you computed, assuming the null is correct. So let's write that down. So it's the p-value, the definition of it is the probability of drawing a test statistic as least as adverse to the null hypothesis that you did as the one you computed, assuming that the null is true. So to compute this p-value, we need to know the sampling distribution. So we need to figure out the distribution of this test statistic that we want the p-value of. You know, in general, this can be complicated if n is small. You know, but if we can imagine the sample size getting large, so if as n kind of goes up, maybe we can use the central limit theorem. Can use central limit theorem if n is large. So remember, that kind of means that this normal distributions as n goes to infinity. So you know, that definition is seems really complicated. So let's kind of get an idea of what we're doing here. And so let's say, for instance, that we know that this random variable is distributed normally. So if y is normally distributed, and let's say we don't know, the population variance, which is going to be true in kind of all the applications we have. So what the p-value is doing is kind of, we have this distribution of our test statistic. So this is the distribution of our t statistic, and it's in particular the distribution of this t statistic that we talked about before, where we, take our y bar, our sample mean, we're going to subtract this hypothesized value, and because we don't know the population standard deviation, we're going to use that standard error that we calculated before, in the videos before. And if y is distributed normally, that means the distribution of this t statistic is, centered around 0, and it follows a t distribution with n-1 degrees of freedom. And so what the p-value is, it's calculating the area, to the left and to the right of, the absolute value and the negative of the absolute value of our t statistic. So what we're doing here is we're, computing our t statistic. So this is, the negative of the absolute value of our t ratio, or t statistic, same thing. And we have, the absolute value of our t statistic over here, assuming it's a two-way test again. Sorry, we're assuming it's a two-way test. And what the p-value is doing is it's calculating the area to the left and to the right of this t statistic using this t distribution with n-1 degrees of freedom. So that's basically saying, what's the probability that we got a t statistic, this far away from 0, and that the null is true. And if that's really, really low, then we have a really, low chance of committing a type 1 error. And so how to think about using this to come to a conclusion of your test, what we can do is can compare this p-value to the significance level that you chose in that kind of second step, which we often denote with that alpha. So if this p-value is less than alpha, we can reject the null. And if this p-value is greater than alpha, we fail to reject the null. So this is essentially what a p-value is. And so above we're kind of assuming that we know that y is distributed normally, but we don't know the population variance. Well, we can even go a step further and say, what happens if we, don't know how y is distributed normally and we don't know the population variance, but we know that n is large, or we can assume that n is large. Well, if that's the case, then we can use the standard normal distribution instead of the t-distribution, because asymptotically we have this normal distribution. So let's just write that down here. So if distribution of y unknown and the population variance unknown, we're kind of carrying out the exact same steps to find the p-value. We're just using a slightly different distribution. So now our t-statistic under the null has a standard normal distribution rather than a t-distribution with n-1 degrees of freedom. So now this is a normal 0, 1 distribution if this is our t-statistic. Our t-stat equals, y bar minus whatever your hypothesis value is over the standard error of y bar, just like before. But now if n is large, that's supposed to say n. If n large, as we discussed before, then the t-stat is distributed normally. Put a little a there for asymptotically, 0, 1. Because we're subtracting the mean and dividing by this standard error, or you can think of that as like the sample standard deviation. So then we're coming up with it the same way, where we're kind of getting the negative and the positive version of the absolute values of our t-stat or t-ratio. Missing a minus sign over here. So we're doing the exact same thing, but the distribution that we're kind of using to come up with this p-value is different. And it might be a little more familiar to you because it's like a normal distribution rather than a t-distribution with n-1 degrees of freedom. Again, to come up with the conclusion of, the conclusion for our hypothesis test, we're still just kind of comparing this p-value to the significance level. So really to compute these p-values, I'll just shade this in to say that this is the area we're computing. Really to come up with this p-value, we need to take some integrals and things like that, but this is what Stata does for you, or these different statistical programs do for you. They give you the p-value. And the p-value gives you so much more information than just kind of like, rejecting or failing to reject at different significant levels, right? It's telling you the exact significant level, gives you the exact probability that you're making a type 1 error, I should say.